Yeah, till now we saw those things which are fundamentally important for us. In electrostatics, we saw Coulomb's law, force on a charge, electric field intensity, and then other way of representing electric field intensity, flux. Then taking flux, Gauss law, Gauss divergence theorem, all these things we saw. Definitely, Gauss law, Gauss divergence theorem are the topics of interest for us because they are there in mathematics as well as they give us third Maxwell's equation. We know that every electronic system, for it to work, we need to supply electrical power to it, or we need to bias it. We need to apply a voltage, is what we know. Whenever we want to apply a voltage, that means create a potential difference between reference earth and the supply voltage, we will take a cell. And that is basically, that creates the potential difference between 2 points in the circuit. When we apply this voltage as a supply voltage to the circuit, current starts flowing through different branches in that circuit. And these currents can be determined by knowing the volt ampere relations of different components in the circuit and the fact that some of the voltages around a closed path in any network or circuit is always equal to 0. In physical networks, that happens. It's voltage, voltage, voltage everywhere for us. So, potential difference as a topic is practically very important. So, the topic is today electrical potential difference, but I will write it as potential difference first. Then we will come to potential actually. It's better for us to come from mechanics and physics, where we speak about potential energy. Tell me first of all, what is the potential energy of an object? Here also same, that object is electrical charge. But in physics, in mechanics, we should have studied actually something called as potential energy, kinetic energy, work energy principle. What is potential energy of an object?
Energy because of force.
It is
The energy possessed by an object by virtue of its position.
By virtue of its
Position.
position only.
Configuration.
Universal definition. Position also. Other than that, energy possessed by it by virtue of its, here it is properly, its position or state. Correct? It is very important for us to understand this for the sake of potential that we want in electrostatic fields. State is what? At rest only, wherever it is, deformed elastic member, spring, for example. Position that you know. Very, very important for us. Listen carefully. If somebody says there is an object of mass m at a height h above Earth's surface, wherever it is, at a height h above. If there is a mass m, what is its potential energy?
MGH.
MGH. Keep listening. There is a spring. And now undeformed spring, formed and kept. It will not have any energy. But the spring compressed so that the length decreases by x, or expanded so that the length of it is increased by x. We say that it stores energy. Maybe half kx squared, correct? Where k is the spring constant. Correct only. In both cases, energy possessed by the spring is kx, half kx squared. When it is not deformed, compressed or elongated, it has no energy. Very, very important statement is there to be understood here. Why it is mgh, if somebody can tell me? Actually, there is one principle called as theorem, actually, work energy theorem. If W amount of work is done on an object, that amount of work done will get stored in it in the form of energy. Here, if you move it without deforming it, I can push it. Keeping it on a horizontal table, I can push it, do the same amount of work, because of which I apply force. That force creates acceleration. That creates time varying voltage, velocity. Because of its mass, at the end, it will be having W joules of energy in the form of kinetic energy half mv squared. If it is deformed, it will have potential energy half kx squared. To deform, we need to perform the energy work. Work done is always equal to energy. Is basically work energy theorem. It either gets stored as kinetic energy or potential energy, or in some cases both. Some part of it is kinetic energy, some part of it can be potential energy. When it is potential energy, please understand now. Here, normally work done, when we say somebody has applied force on it and did some work on it. When a spring constant K is deformed so that its length changes by X, in the deformed state, it stores potential energy. Please see here. In the deformed state, it stores the potential energy equal to half kx squared. You will not ask who deformed it, how much of force was applied to deform it. I also will not ask. Somebody says it is elongated or compressed by x, I will immediately say energy stored in it is half kx squared. Who deformed it? How much of force that person applied on it? Unnecessary for us. In this case also, mgh is the work done. But nobody will ask us who brought it here to calculate the potential energy. No. In which path it came here? Here also, what are the sequence of operations performed on it so that this is now the position of it? We don't ask. Current state is sufficient for me to talk about its potential energy. Here, I will give a statement, very important statement. Potential energy work energy theorem only is the amount of work done against an opposing force. How much work is done against a force is important for me. How much force we applied is not important. How much of force is applied is not important here. It is the amount of work done against an opposing force. Here, if you look at it, careful. When it is taken along this path, let us say straight line path only. At each and every point along this path, mass m will experience the force in the downward direction equal to mg. Against this mg, I moved it through a distance h, because of which the work done on the mass of on the object of mass m against its weight is mgh, against the force of attraction from Earth, against the gravitational force. mg is trying to pull it down. You moved it by h in the opposite direction to the force. mgh is not the work done by us. mgh is the work done against the opposing force mg when it is moved through a distance h. Please understand this. Here also, how it is kx squared? K is the spring constant of the spring. Integral kx dx, no? Why integral kx? Chandrika, please tell. Good. You are there at it.
Force will be kx, sir, and displacement will be dx. So
What
total
force
work.
is kx? What force is kx?
Spring force, sir.
Oh no, what is that? What is the specific name of it? It's an elastic member. When you try to deform it, it exerts the force against deformation. What is that force called as? Restoring force. Correct? The force developed inside the elastic member to oppose the agent which is deforming it is a restoring force.
Okay.
When a spring is deformed by x, elongated or compressed, when it is compressed, there will be a restoring force developed in this particular direction by kx. Proportional to x, proportionality constant is spring constant. When it is elongated, in this direction, kx is developed. K capital X, kx is actually ultimately the elongation produced. In the middle, let us suppose this is capital X. At any displacement, the extension or compression of x, small x, there is a restoring force kx. Against that, you deform it by dx. Integral kx dx is the total thing from 0 to capital X. Is definitely half kx squared. Please note that The energy stored in the spring is the work done against the restoring force. If it is a linear spring, earlier we had no alarm timepieces. No, we need to give the key. There we basically coil it. It uncoils. No, there we rotate it. Means what? We apply the torque and rotate it against the restoring torque. And when it unwinds, actually, it basically runs the clock. Please understand one particular point. Potential energy actually is what? The amount of work done against an opposing force. The amount of force that we apply doesn't matter. Given a spring constant K, whether a small kid compresses it so that the length change in the length is X, or a heavy strong man compresses it so that its change in length is X, energy stored in is fixed. And you know very well that the amount of force that kid applies is different from some heavy person applies. Here also, in MGH also, who lifted it doesn't matter for us. Against a particular force, there is an opposing force, like restoring force in this elastic member. Here there is acceleration due to gravity. Please check it. Against something, you move or deform, potential energy gets stored in it. Against the frictional force, if you work, it gets converted into heat energy. It will not get converted into potential energy. Field, there should be a field here. Carefully look at it. Now, it is very easy to understand it through the potential difference of an object when it is moved from one point to other point. We will straight away take it into electric field, define it, and start talking about electrical potential difference. So, I think the only way in which you can understand it properly is through gravitational field and gravitational potential energy. Please check it now. Amount of work done against an opposing force. If we do the work, if you don't do the work, field will do the work. Keeping an object at a particular height, if you leave it, gravitational pull takes it down. When the gravitational pull takes it down, its height is decreasing, its potential energy is decreasing, it gets converted into kinetic energy. In fact, anyway, because of the force accepted, acceleration comes into picture, velocity, kinetic energy, automatic. If you lift it up, it gains kinetic for potential energy. Correct? Check it now. When we do the work against the field force, if the work is done against the field force, the object gets potential energy. Potential energy is non-negative. Energy is a non-negative quantity as such. Correct? Energy non-negative? Energy non-negative? Can energy be negative? Hey, can energy be negative? Can potential energy of an object be negative? Electrical potential energy can be negative. Can mechanical potential energy be negative? We'll see. Okay. Gets potential energy equal to the work done. Positive it should come. If the field does the work, it gets negative energy, negative potential energy. Change will be negative, of course. Potential energy, positive potential energy in this particular case, increases if we do the work, decreases if the field does the work. Please check one particular point. The reference position is on the surface of the earth. If you take this object of mass m straight up to a height h, everywhere the opposing force is mg in the downward direction, assuming acceleration due to gravity remains constant with height in that particular range. And the displacement produced is h in the upward direction, mg bar in the downward direction, mass is scalar. Acceleration due to gravity is in the downward direction. When it is displaced through a height h vertically in the upward direction, yeah, that is h bar. Potential energy is work done, correct? Equal to mgh, which is m mod g mod h. And whenever it is work done, please follow this now. It is a dot product, correct? Work is scalar. If it were to be the dot product of mg bar dot h bar, it should have been negative, correct? Right? What is this equal to? Is this mgh? mg bar dot h bar, is it mgh? Where g is the acceleration due to gravity value and h is the height. If it is mg bar dot h bar, it will become minus mgh, no Darshan?
Sir, cos 180.
Mg bar dot h bar, is it positive or negative? Magnitude is mgh only, no doubt about it. Is mg bar dot h bar positive or negative? Tell man confidently.
Here, positive, sir, because work done against the field.
Mg bar downward, h bar upwards. Mg bar dot h bar, is it positive or negative?
In vector, it's negative, sir.
Huh?
Negative, sir. Like mathematically, it's negative.
Negative.
Yes.
But potential energy is
Positive.
positive. So what to do? Minus mg bar dot h bar. This is the only way in which we can come to the conclusion here. Mg bar is downward, h bar is upwards. Potential energy is positive. It is not dot product. Somebody told me that it is work done. No doubt about it. Work done against, because of it is minus of. Work done against, because of which it is minus of. Is what is to be understood here. This actually, proper learning, there only it is minus mgh. Minus mg bar dot h bar. Dot product. Work done is dot product. But When it comes to potential, it is minus. Everywhere. Minus of. Listen carefully. Very, very important things now. This is H. This is the initial position. If the object is taken along an inclined line to the same height, of course, finally, H. Again, the potential energy of this object will be mgh. But this is L bar. Definitely, the length of the path along which it is taken is not h. But because it's ultimately it is taken to a height h, its potential is mgh. Because if there is an object above the Earth's surface at a height of h units, I will immediately tell. I will not ask the previous story at all. How did it come here? We will not work whether it did it come from up or down. Right? We will not ask about it at all. If it is there at a height h, we will say it is having the potential energy mgh. This is L bar is the displacement vector. Carefully look at it. At each and every point, when the object is moved along the straight line path, at each and every point, the weight acts vertically downwards. Correct? And the amount of force opposing my motion is mg along the line. If this is theta, it is mg cos theta. Everywhere mg cos theta is trying to oppose the motion of this object along that line. My opposition is only mg cos theta. Mg cos theta in this direction, L bar in the opposite direction again. Mg cos theta is the component of the force. This is actually F bar opposing it along that particular line. The opposing force is only F bar. I moved it through a vector of L bar, because of which it is minus F bar dot L bar. Is what again? Mg cos theta into L. Magnitude of F bar is mg cos theta at each and every point along this line. F minus F bar dot L bar, sorry, F bar dot L bar here. Because of which it is mg L cos theta. What is this L cos theta? What is this L cos theta? What is this L cos theta? Height. L cos theta is height. You agree with this? Cos theta is adjacent side by hypotenuse, right?
Yes, sir.
L cos theta is height. Effectively, to which height I took matters. Whether it is straight up or along a straight line path where the amount of opposition is everywhere same, given by F bar in the downward direction along the line, of magnitude mg cos theta. It's actually F bar dot L bar minus F bar dot L bar. Hey, you understood this minus mg bar dot h bar? Angle between these two vectors is 180 degrees. Dot product is actually a bar dot b bar when the angle between them is 180 degrees is what? Mod a, mod b, cos 180 is minus 1. Minus it will come. Straight dot product will be minus if the angle between the vectors is 180. I want to convert it into positive because I am getting positive potential energy. My interest is to look at positive potential energy acquired. Because of which the general definition is minus mg h bar. Potential, whenever I say it is minus mg bar h bar, dot h bar. If h bar is in the direction of the weight, now it loses potential energy. This will tell that the potential energy that it gets is negative. That means the change will be negative. Last case. This is equal to what? Minus f bar dot L bar. At each and every point, f bar is in the direction opposite to L bar. Of magnitude mg cos theta. Now listen. This is what is the other case. I will take it to the same point at a height h. But the path followed is this. Path followed is this. We'll define it only for positive change. Then what to do? What is that? What is happening here? The angle between the displacement vector and the restoring force is always 180 degrees in the first two cases. Here, because the curvature is changing, initially the component is small, right? Finally, the component will become larger. Correct, no? The component opposing the motion along that particular path will change from point to point because its curvature is changing. I think you appreciate the fact that if it is taken along this line, the opposing forces x, let us suppose. If it is taken along this line, the opposing force, will it be smaller, more? Hey, this is x1, this is x2, opposing force. Which is more? X1 is more because slope is more, right? You go to Tanjavur, there is one Brihadishwaralayam. And it's actually a marvel, actually. People really they thought a lot about it initially. There is a big spherical stone on the top of that, right? And there were no cranes and all. How did they lift and all? People, they constructed a ramp from a nearby village and slowly pushed it onto that particular level. Because the slope is less, the opposing force was less, no? They constructed a ramp from nearby village to the top of that temple and then they pushed that slowly, right? So when the slope is less, restoring the opposing force is less. Ultimately, it goes to the same height, let us suppose. Here, what is happening here? Slope is changing from point to point because of which f bar itself is changing. when F bar itself is changing, we write the expression as what? Now from point to point it changes, because of which it is integral F bar dot DL bar at each and every point only. I cannot straight away take the dot product and say this is what is the value. Now, either F is changing from point to point, that's what is the non-uniform field case, or the angle between F and DL are changing from point to point. In both cases, we cannot just take the dot product and say this is the potential. I have to divide it into so many small parts. Along each small path, the restoring, because the slope is different, the restoring or the opposing force is different, because its component is to be taken along that particular path, and then move it through a DL. By the time you change the DL, again the direction of it, no, the curve path got changed. The slope of the curve got changed. Because of which you have to talk about when it is the potential difference minus F bar dot DL bar from A to B, from initial position to final position. The same F bar dot DL bar, last point. If I say the path taken is this from A to B, should I get positive answer in the Earth's gravitational field? If I take it in this particular path, the change in the potential should be negative, because you need not do any work. You just show the path and then leave it. It will come down by automatically because of the weight. You need not do any work here. In the same field, F bar dot DL bar along this path is positive. Ultimately, it should come out to be positive value. In this direction, it should come out to be negative value. Because it is minus F bar here also, if I leave an object here, it comes down because of the weight. What is the change in the potential energy? Minus mg bar dot h bar only. H bar is downward now. Angle between mg bar and h bar is what? 0. Minus will remain as it is, because of which it is minus mgh. Change in the potential energy is negative. That is how we normally calculate, use the principle of conservation of energy. One object of mass m is dropped from a height h. What will be its velocity by the time it reaches Earth's surface? How will I calculate? Initially it is mgh. Ultimately, entire mgh got converted into half mv squared. Because potential energy became equal to 0. Principle of conservation of energy told me that it would have converted into kinetic energy. It has come down because gravitational pull pulled it. So the velocity with which it strikes the ground is root 2c. If it comes down, it should lose its potential energy in the gravitational field.